to everyone, you can start following basically on your computers. One thing that I recommend to everyone when you follow this, if you need more time, please just tell us that you need more time. You can unmute yourself and actually ask it, because sometimes it's too fast and then people a bit lost. So, but we don't know unless you complain, right?
Yeah, absolutely.
Okay, let me
so you can stop me at any moment. I'm gonna leave it running just because we can run everything and just walk through each one of these steps and analyze each one of these steps separately, just so that all the training may happen in the meantime while I'm explaining here.
Right. I'm trying to also run it.
Hopefully everyone can access the Google Colab as well.
Well, there are some problems in China. But in
principle, I'm sorry if I didn't.
But there is no good solution to it, I guess. So we'll just we'll just go on. So I'm also starting now. So let me just let me first follow it so that we have some. Okay, so I need to choose GPU, right?
Yes, choosing the GPUs will be better. You can, like for those who are following and seeing here the slides, you can just go to runtime and change runtime type and select the GPU accelerator, which is going to make the training much faster.
All right, so let's go on. So I am trying to follow in exactly what you're doing. So what you now finished the first step, right? So installing.
Yes. So I just ran everything for now, so I can walk you through the process of what I'm doing. First, you're gonna see that the tutorials are also available, and the package is also available in this GitHub repo that I put in the chat, right? So if you would like to check the actual code later, you can have a look at it. If you want to see an interactive explanation of everything, you can just go to this link that I'm also going to put in the chat.
Yeah, please.
It's perhaps an easier way to follow what is going to be the adversarial attacks and how do they work and so on and so forth.
All right. So I finished my importing and installing. So now that was cell 2, right? I think we can go on to the next one. So everyone is following, or does anyone need more time?
Yes, I can follow.
Okay, great. So please go ahead.
Awesome. So first, everything that I'm doing here is just installing the GitHub repo so we can use the helper functions, and Google Colab already takes into account all of the dependencies, like heavy ones like PyTorch and so on. So for the first example, which is the 2D double well, I'm just going to reproduce what I showed you in the presentation, right? I have a couple of helper classes that implement this forward pipeline and the active learning loop for these very simple potential. And because the evaluation is instantaneous, I can actually do an active learning loop at here in real time so that you can follow. Of course, it wouldn't be possible to do it for a DFT, which is why I'm going to show later how to sample new geometries using another pre-trained neural network intercom potential.
So basically, robust is your module which we just installed, right? So robust is your code. Okay, just to everyone.
Yeah, so it's the code. It's the code in this GitHub repo over here.
Nice.
Yeah, so you're going to see all the code is here in this robust. It implements all the things you need to reproduce the paper and a couple of helper functions. It's important to note that you don't need this robust package in order to implement adversarial attacks. So in the second part of the tutorial, we're actually going to implement all of these adversarial attacks for the ANI models.
All right.
And you're going to be able to see it's very easy to follow, hopefully.
Yeah, thanks.
Yeah, so just for the toy example, I proposed a functional form of the 2D double well, which you can see over here. I create a masked double well, which basically means that I take off the second well, or just take one of the wells to start with, and sample new configurations. Based on a random data set. If you plot it, you're going to see exactly what I showed you during the presentation. Here's the 2D double well with the functional forms that I proposed, and each one of these white points is one of the new training points that I randomly sampled for these well. Of course, if we are talking about actual chemical geometries, and if this was a potential, then the sampling is not a sampling that corresponds to the Boltzmann distribution that we were expecting from this, but it's okay. This is just for the purposes of the training of the neural network and showing how the active learning loop works.
So you use the mask just to concentrate the training in one side of this double well.
Yeah,
the mask
because exactly, because what I'm doing here, I'm basically sampling. I'm sampling an XY range over the entire range of the plot, which is from minus one, more or less from -1 to +1, right? And so what I basically want to do is I want to take into consideration only the points in one of the wells of the 2D double well. So it's just a helper function to do that, but you could do it manually if you wanted, because we know the positions of these wells. Instead of doing it manually according to XY positions, I just set up an energy threshold.
Okay.
According to these units of energy over here. So
Perfect.
that's the energy threshold. I don't want anything above -2 in our potential.
Okay, great. Thank you.
And so we can do the kind of analysis and set up all the training parameters that I showed you before. For example, the temperature of sampling. Temperature is the KT for the adversarial sampling. In this case, we have energy coefficient, forces coefficient. And for this example, we can train very simple feed-forward neural networks with, you see here, 4 layers, about 1,000 neurons in each hidden layer, and so on. Learning rate, number of epochs for the training, batch size. And here it's important to note that the adversarial attacks also have their own learning rate. And the learning rate basically means how fast you're going to move these input coordinates. Simply because the adversarial attack is basically making a back propagation, taking the gradient of the uncertainty, the weighted uncertainty according to those terms that I mentioned before, with respect to the input coordinates. So that's what you have here. In this toy example, just for simplicity, I'm going to use the pipeline and the active learning classes that I have in the robust package, and create this active learning loop. So this is very standard, right? What we would expect from a traditional active learning loop and a traditional training procedure for any neural network example. We're going to minimize the train loss, and then after each one of these generations, we're going to attack. And each one of these attacks basically means that we're going to sample new points. And I do this over and over, okay? And in the end here, it ended up not converging exactly to the point we wanted, but that's okay. You're going to see that when I plot the results, or first initial understanding of how the 2D double well works is this at the top. I'm plotting here in the second row what are the new points, the existing training points in white, and the new sample points in red. And then I keep sampling new configurations according to these uncertainty landscape. And as we sample these points, you can see that even with as few as 6 points on this side over here, we already start to predict the 2D double well better. So this is an iterative process. Perhaps the bottleneck is really implementing the active learning loop, especially for density functional theory calculations, but and retraining the neural network, of course. But for many examples, it might be more efficient to do this simple retraining in the simple sampling rather than performing 1,000 density function material calculations to sample new regions of the configuration space. Of course, your results as you run this tutorial, your results may look different than this, and that's because of random seeds, initializations, and training, and so on. So this already gives you a bird's eye view of how the adversarial sampling works and how can it reproduce the results that are shown in the presentation and in the paper. But of course, this is just for a toy example, and perhaps it's not interesting, and perhaps it doesn't work for your particular neural network interatomic potential, and so on. So to try to address these things, I wanted to show you how to perform adversarial attacks on molecular systems and implement all of these functions from scratch. So I'll try to spend more time in the second section than in the first section. But before we go to the second section, I wanted to check if you have any questions or any standing issues about this.
So basically, can you scroll a bit up? So there is this attack, and then you have evaluating attack. So evaluating attack is normally, so in your case, it's basically, you need to label, right? So you say like DFT, for example, DFT calculations. So evaluating attack is basically—
It would be a DFT.
Okay.
Yeah, it would be a DFT calculation. In this case, it's just taking the XY coordinates of the new point and verifying what is the energy. So this toy example is very very useful in this case because I can do it in real time as you see, and not necessarily run an actual DFT calculation.
Yeah, sure. So I finished my active learning. Now it tries to plot, and for some reason it's quite slow. It's
very slow. It's actually very slow because I'm evaluating all the PES for each one of these steps before plotting them. So that's why it's a bit slow. But hopefully it will show up very quickly.
Daniel? I just have a very naive question here. Do you know how this approach would compare, if it's comparable with the Bayesian neural network approach, for instance, where we have, in principle, this uncertainty built in the model? So they are kind of comparable, or there is some advantage from these adversarial attacks?
Yeah, it's a very good question. Bayesian neural networks have to sample distribution of weights, right? And by sampling distributions of weights, you're getting an uncertainty because in principle you have some distribution of models to model that particular function of interest. What I want to do here is really to get some differentiable mapping between input coordinates and uncertainty in the end. So in the case of Bayesian neural networks, this might not be immediately possible unless, of course, you're sampling different models and then, performing all these forward steps during the sampling process, which is exactly what we do in terms of an ensemble of neural networks.
Okay.
Cool.
Thank you.
Also, all of my calculations finished actually, so that's kind of nice.
Excellent. So hopefully you can see already some progression that might look different from here, but you can see that each one of these rows, the top row is the prediction, the second row is the prediction with the data points, so you can see what are the training sets. The training set is in white, the new sample points are in red. The third one is the variance of forces. You can see brighter regions or regions with higher uncertainty. And the fourth row is the variance in forces, but also weighted by the energies, as I showed before with that Boltzmann-like term. So you can see that these new sample points try to go towards points that maximize this adversarial loss function. And those are hopefully points that are the most informative for sampling and for retraining your neural network. Cool. So this is the example that I showed in the presentation, and that you can look at, and you can play around with the parameters such as temperature, number of neural networks, and so on and so forth. But if we're interested in doing that for molecular geometries, you're going to need your own architecture, neural network computational architecture, your own data sets, and so on. So you can do, in principle, you can use for any system. In the interest of time, we'll just focus here on the Torch-Ani model and data set, because it's easily available. It's easy to implementing these systems, but of course you can do it to your favorite neural network potential. So in this particular cell, in the second section of the tutorial now on the adversarial attacks on molecular systems, I'm going to basically install Torch-Ani and some tools for visualizing like ASC and Py3D model, and download the actual data sets for these systems. So hopefully if you're able to download all of them and extract, and of course use a Py3D model and enable the widget in Google Colab, you can again perform all of the imports and that are relevant for the second part of the tutorial. And this is written in such a way that you don't need to run the first part of the tutorial if you wanted to skip that. And then load all of the data and models for the Torch-Ani models. So of course, if you're familiar with Torch-Ani, you're probably going to see a couple of things that are involved here, such as energy shifter and how the data is represented in their system and stored with these H5 files and so on. I do not want to spend too much time in here, because perhaps it's not the main point of the tutorial. What I wanted to show though is that I have a data set, and I can show you here how the data set looks like. In this particular case, it's just a list that contains, what are the species. In this case, the ammonia molecule. Again, in the interest of time, not because it's the only one that works with the coordinates of the system and a particular energy that is predicted with their level of theory. I think this is for the CCSDT. And because I already loaded pre-trained models, I loaded a set of 8 models to make this particular example. These are just very convenient things that the Torch-Ani and Ani team made available for us to use straight out off the shelf. But now the interesting thing is we want to implement the adversarial attacks from scratch. So I skipped the whole idea of importing everything from the robust package, and I rewrote the class that implements the adversarial loss. It could be any kind of loss function, any function that you wanted. But really what I take into account is a set of energies, which are the energies in the training set, and a parameter of temperature, as we have before. So the temperature indicates how high in energy we want to go in terms of the new points which are sampled. And each one of these methods here is going to give you, like, of course, the Boltzmann probability, the partition function of your training set, and what's going to be the probability of sampling a new predicted energy. So you can see here, we calculate the Boltzmann probability and normalize it by the partition function. And finally, we calculate the actual loss function, which is the variance of the forces weighted by the probability of sampling these new energies. Okay. And because we want to predict the forces directly from the energy, we can use the autograd to actually perform this kind of backpropagation to obtain the forces from the energies with respect to the coordinates. And here's one of the important things that if you want to implement it, if you have your models in PyTorch, you're going to have to look at, which is to set retain graph equals true, because that's basically going to keep your computational graph in the memory, so you can backpropagate the uncertainty with respect to the coordinates, and not only the energy with respect to the coordinates. The uncertainty is usually built on top of variance of forces. So once you get the forces, you get the variance of the forces, you backpropagate that to get the displacements. So hopefully this is not too alien to everyone who's in the call and who's a bit more familiar with PyTorch, how PyTorch works and how to implement these neural network interactive models.
Yeah, that's okay so far. Yeah.
Okay, good. And now, like, once this function is implemented, once the loss function is implemented, we can proceed to actually create this loss function that's going to be used in the attacking loop, and using some data, which is just a subset of the data set over here. Okay, so I'm basically taking the ground state geometry, although it could take just a random sample of my training set. Yeah, so this is an interesting point, which is adversarial attacks need an input geometry to start with, right? So I basically take an input geometry, and then I displace this input geometry to obtain my new sampled geometry, my new sampled conformation. So I just need an input structure. In this case, I'm selecting here for this tutorial the ground state geometry, but it could be any geometry, and that's going to lead to different explorations of the PES. In the original paper, we used a random sample of the training set to perform that exploration. So that's what we did. If you look at it now, if you scroll to this cell number 19 over here, you're going to see the actual loop for performing the adversarial sampling. And I'm going to do it for each batch. In this particular case, you can see here that the batch size is 1, and I'm going to do it only one attack, that is for only one geometry, for simplicity in this tutorial, so that I can show you all of this without unbatching and dealing with these different systems. So what I do here is, to do the adversarial training, I will first take the coordinates from the batch and set that it requires grad equals true, which is going to be the important part for calculating not only forces, but also the uncertainty, right? And then I initialize a delta, and delta, if you remember, is the initial perturbation that will apply to the input geometry. If I may show you the picture, this is the delta that I mentioned in the code. I basically have to apply an input perturbation to the input coordinates of your molecular geometry. And what I do is I backpropagate the weight and uncertainty with respect to delta, so that we optimize delta in order to obtain this sampled conformation. Okay, which is why I need, again, requires grad equals true for this particular delta. And delta is the only parameter that I'm optimizing here. So if you look at the
what is this 0.001 that you put this coefficient?
Yeah, exactly. So this is, I'm just initializing delta with a very small random numbers, right? So that look like the coordinates of your system.
Okay.
So it's as if we will apply the tiniest perturbation in your input coordinates. You can start with 0 perturbation. All delta is 0. What happens then, it becomes very deterministic. Every time you do the adversarial attack, you're going to end up in the same point, because your input structure is the same and the whole process ends up being deterministic.
And at the same time, you don't want this coefficient to be very large, otherwise you start from some physical geometries or some large perturbation. Okay.
Exactly. So the whole point is, I don't want to perform a random sampling of my PES, right? I don't want to displace the atoms super far away from their ground state geometry. I just initialize them with a very small number so that the neural network can tell me where it wants to go.
Okay.
Or where the geometry actually maximizes the uncertainty.
Nice. Perfect.
Maybe I'm jumping ahead, but basically you don't want to calculate again DFT, so you basically find some structures which are similar in the data set after you perturb them? Or...
Yeah.
Okay.
Yeah. So deduplication definitely happens. But the interesting aspect is that because the neural network is trained on that particular train set, its uncertainty tends to be small for points that it's trained on. So that means that higher uncertainties usually relate to points which are already outside of the training set. Yeah. So that's why you don't need all of these post-processing steps to deduplicate the input configurations. So basically, by maximizing the uncertainty, we're already driving the geometries away from the training set, because the neural networks inform us what's outside and what's inside the training domain.
Yeah, but now you need to label them. So
yeah, now eventually we need to label. In this case, in this tutorial, I'm not going to label. I'm just going to show how the sampling is performed, because of course then everyone can label by doing the FT calculation, right? I'm not going to retrain these ANI models. I'm just going to show how we can sample new geometries through these
basically the
processes,
very
which hopefully
first epoch of active learning. Okay.
Exactly,
Cool.
Exactly. Because hopefully, you know, all the active learning loop can be implemented for based on your own needs and based on your own systems. But over here, you can already see, to get a feeling on how to implement that, it's going to be the same for all of these models, especially if implemented in PyTorch. Basically, one of the most important steps is this. We're going to create this delta function, and then for each one of the epochs, and this is an epoch of the adversarial attack, because it's an iterative process, we have to do it step by step, exactly as it's done in the adversarial attacks community for neural network classifiers. We do each one of these perturbations, changes in the perturbation step by step, and each one of these steps is an epoch. So what I do is I take my final coordinates of the system will be equal to the initial coordinates of the system plus a perturbation. In the beginning, on epoch number 1, this is going to be the very tiny perturbations. So the actual coordinates are going to be very similar to your initial coordinates of the system, which in our case is the ground state geometry of the ammonia molecule. And what I do is I take the results in the Torch ANI package. What I do is I basically take each one of these models and give it the species and the coordinates of the systems. And these are the disturbed coordinates, as you can see. I can predict the energies, and then I normalize it. There's a whole bunch of steps in terms of normalization here, which you can see, but are not super relevant for this particular adversarial attack strategy. It's just for you to see the actual energies in the end. But you can take the energies, you can take your predictive forces, and these function forces from energy is exactly what I showed you before. It's this one over here, in which we use AutoGrad to compute the forces from the energies with respect to the coordinates, which is basically taking the grad of energies in order to compute the forces. And then finally, we pass these predicted energies and predicted forces to the loss function, which is the adversarial loss we initialized before. Adversarial loss is going to compute it all by itself. And then we can do exactly as we do in the training process, but this is an adversarial training. So basically, we're maximizing the loss in a process and taking a step. Okay, so now just here, down here, I basically save each one of these metrics. So for example, what is the norm of the forces? What's the standard deviation of the forces for these batches? The mean, the standard deviation, the maximum of the standard deviation, and so on. So I showed here that I did it for 60 steps. I can do it again for you in a moment if we want to go there. And I can, but I wanted to show you how the trajectory looks like and how the sampling looks like. So in blue over here, I have the energy of your new configurations with respect to each one of these attack steps. What we're doing is we are maximizing the force, which is this red curve, which ends up, of course, driving your configuration far away from the training set. But as we increase the number of steps, you're going to see that this ends up converging, because we're already finding maximum of energy in our system. Sorry, a maximum of uncertainty. Yeah.
I was wondering if it is possible somehow to add, let's say, some kind of constraint that enforce this sampling to go into a given direction that you want to sampling more during the training, because you as I understood, the sampling is driven by the uncertainty, right? But
Yeah.
I was wondering if it's possible to add some other constraint. Let's say you want to sampling more from another minimum. There is a way to do that or not?
Yeah, you're right. There are two ways to do that. One of them is to pass already the input configuration that you want. So I'm just choosing the ground state geometry. But if you have a prior knowledge and you want to start, for example, from a particular data point that's closer to what you want, you can start from that data point. You can just pass it here as the seed geometry. The second thing you can do is you can change how delta is created. So what we did in the case of alanine dipeptide that's shown in the paper is that the alanine dipeptide has the two dihedral angles that are of interest, and they act as some collective variable. So we want to bias or adversarial sampling also with respect to these rotations, right? So you can just implement the rotations of the whole branches using these differentiable functions using PyTorch. And then delta doesn't become simply a displacement, a translation with respect to the input coordinates. It becomes also a rotation with respect to these angles.
I see.
So
then you can bias the sampling.
Yeah.
Okay. I see.
Of course, the translation is, of course, the translation is the simplest case because then it's very easy to see over here, right? So if you just scroll down, you can see the energy, the standard deviation of the forces, and here how the sampling looks like. And because Google Colab doesn't work well with NGL view and so on, I just implemented this as a tiny movie. It's basically just repeating the same thing. What is happening is the input geometry is the ground state, and you can see that the sampling moves the atoms just the tiniest bit in such a way that this angle is more opened here. This vertical position of the hydrogen atoms are closer to the nitrogen atom in the center, and this already leads to a configuration that's very high in energy, I would say, in like over 100 kcal per mole of predicted energy, but it wasn't existing in the training set. Didn't exist in the training set. Why this matters? In the case of Ani, they sampled their training set really well in order to predict this. So going towards very high energies is the only way to go in order to find points of maximum uncertainty. You can, if your methods or if your training set is not as diverse and it's not as complete as the Ani training set, you may find points which are much closer to your initial geometries and still confuse your neural network by a decent amount. And that's the original motivation, to find those points that confuse your neural network potentials by a decent amount without having to go through the MDE sampling that will be just a forward loop and brute force through all the configurations until you find something that confuses it. Yeah, but this is the overall overview that I wanted to give you. You can find many more tutorials in the GitHub repo and a bit more detailed explanation in the paper, but hopefully this tutorial helps you understand how to implement the adversarial strategy for molecular systems using these backpropagation techniques and the adversarial implementation of the adversarial laws.
Yeah, sounds really cool. So I have one more question, because you done it basically for PyTorch, and Ani is based on PyTorch, so it's kind of okay. So for all other, so you actually showed impressive collection of your different attempts for different networks. So you're now basically focusing on PyTorch. I mean, we have ourselves, like with Max also, made lots of interfaces to different machine learning potentials. It's kind of a nightmare because everyone has different ways to do it. But on the other hand, you showed many of the neural networks. I expect you had lots of time spent just trying to adapt your code to every neural network, or is it simpler than I think?
No, it's not simple. We actually spent a lot of time doing that, implementing our own code base for example, the Schnet model that's shown over here, the Torch Ani packages, and just for demonstration purposes, we didn't use them in production. But yeah, it's a lot of work to re-implement them, which is why I just wanted to show you like how to do it in few cases, so you don't have to actually install the GitHub, like the new package, robust package, and use its pre-made libraries. If you want to implement it in your own code base, you can just copy and paste whatever is here to implement it in your own systems.
And of course,
but yeah, it's and yeah, it's really a nightmare to re-implement things, re-implement code, and make it accessible to the community.
Yeah, great work. Really appreciate this. And I think
thank you.
It's something very important for the community to provide such codes and tutorials, especially to show how to use it. And yeah, thank you very much.
Yeah, thank you. And I think this seminar series is a great example of an initiative that helps propagate information through the community. So thank you for the opportunity and invitation to be here.
Yeah.
All right. Any final remarks from people or questions?
I see a question in the chat.
All right.
Let me see. Yanqi is asking, since they can mean many DFT calculations, can we use smaller training set white points in generation 1? They look crowded compared to attack points. Yeah, you can play with this tutorial and try to go over here and reduce the number of points that you're sampling. This is the number of points that I'm sampling in particular. You can just remove it and you can say, oh, I want to sample actually just 50 data points. And then the final result is going to be much more sparse. But of course, and the result of that will be, you're not going to be able to even predict the first well before doing the active learning loop. I just chose a high number of data points because I wanted to show confirmations or the exploration towards the second well. But if you want to do it over here as well, you can just change the number of data points and perform the active learning loop again.
Yeah, great. So do you have some, again, you compared many neural networks. Do you have some preference in terms of like what was easier to use, what is kind of more efficient, or like just gives you better data efficiency? I don't know, like any recommendations based on your extensive experience?
Yeah, so like recently we've been studying the most the newest systems and the newest neural networks architectures that are available. NIQUIP is a great package, has interface to LAMPS. The same group from Morris Kaczynski at Harvard, they also developed Allegro, who's apparently, I didn't use Allegro in particular, mostly NIQUIP. That's also a really good package. So these are very highly recommended. Elis Bakatia at Gabor group in the UK, they also have a version that's derivative from that, and like very similar in terms, it's similar in many aspects of the implementation of the equivariance and so on, but they implement the final energy function as a sum of many body terms. The MACE package that they provide is also excellent and is quite interesting one to use. So these two, of course, there are many more. I haven't used extensively all of them. The Schnet package is also extremely well maintained and very, very functional and very good. So that could be another recommendation. The equivariant model Pain, for example, is really well performant to many applications. And of course, there are many more, but I would say these three are excellent packages that we were able to explore and use quite well.
All right, great. Thank you very much. So I don't see, oh no, there is one more in chat, I guess, or even...
Just a follow-up question from Pavlo's question. I don't know if you had to deal with this problem because it looks that in your case you just need the predictions for the model. So as long as the model can give you the predictions, it's fine because you don't need to modify the training loop, let's say, inside of the model. So although Ani is kind of an old generation of these machine learning potentials. As far as I remember, is the only one that you have the flexibility to change the training loop as you want, because they provide for you in the API like the forward pass. So you can build your own training loop in the way you want. So there is some application or some case that you have in mind, or you had to add something new to these potentials?
Yeah, whenever I have to do that, I usually fork the repo, create a local version of a repo, and implement it myself and prototype with it myself. The developers tend to be quite helpful in really clarifying a couple of questions. Like if it's just a prototype at first, they don't push it to the main repo, of course, to create new branches. They just work on my local version. It tends to work really well for all packages, but then it depends how deep you want to go into the code development, right? It can be tricky to just be very deep into the code development process. But in general, it's a good alternative, and I agree that any models and any packages really well maintained and makes it very accessible. It's also one of the reasons why I used it here to show in the tutorial.
Yeah, because Nearkeep, for instance, looks a very good package, as you said, but at the same time has a lot of different parameters. So maybe it's a bit tricky to change for a different system. I don't know, in your case, if it was like find those good parameters for your application.
Yeah, so one of the studies that we're doing in terms of data efficiency and extrapolation trends are really focusing on how a couple of these parameters change the data efficiency of your neural network extrapolation power. So I think there is an overhead, and I think that's normal and happens across the whole field of deep learning, and that we have more knobs to tweak in order to find the best results. And that's perhaps the curse we're bringing onto ourselves in deep learning, that we're finding more and more things to optimize in addition to the infinitely many ways that we have already. But hopefully with some guides that involve, say, loss landscapes or trainability and data efficiency, we can find other metrics to optimize for.
Great.
All right. So thank you very much again. I really enjoyed your both lecture and tutorial.
Thank you.
So thank you for joining us and giving this wonderful tutorial. So let's thank you and wish you a good day. Bye-bye.
Thank you very much.
Bye.
Good evening
Good
for
night.
you and good afternoon.
Bye-bye.
Bye.
Bye.
Bye.